All right, welcome back, Math 30-1 kids. We are going to now solve growth and decay functions using logs and exponentials again. So we did these kind of questions using graphs before. Let's see if we could solve these algebraically instead. Here we're talking about E. coli bacteria culture. It grows at a factor, it looks like a factor of 8 here. So they have a base of 8, so that means if time was 0, we'd start at n naught, and then if time was 1, it'd be 8 times. If time was 2, it'd be another 8 times about that. So the numbers are increasing 8 times as we go. It's a growth function. So what I know about this equation so far, I might as well just kind of sketch out what this looks like. It's a growth function, and it's starting here on the y-axis at n naught. You see that's my initial amount. Usually that's denoted by the a here, but they just used an n naught to represent the initial amount at time 0, which makes sense. Time 0, 8 to the power of 0 is 1. If the initial count of bacteria is 40 or 4,000, and then the expected number, they're just asking, this is a pretty easy question. They want to know what they expect after 1 hour and 15 minutes. So they've actually just given us the time right now. In this case, it was time is supposed to be in hours. I'm looking at this very carefully here. It's in hours. So that means I'm going to change all of this here into hours. So time is 1 hour plus a quarter of an hour, which is 15 divided by 60. So this is 1.25 hours. So that's going to be my time that I'm going to put up in this part here. So n is equal to 4,000 times 8 to 1.5. Punch in your calculator, we get a number. So 4,000 times 8 to the power of 1.5. So I have pretty big number here. 90,509. 90,510 actually, if I round it. 90,510 bacteria. There we go. Okay, so I think we might use the same question here. The patient is feeling ill. The sample of bacteria taken out of the throat. The sample contains 387 cells. 24 hours later, is counted to have found a cell count of 8,012. Find the doubling period of the bacteria. Okay. Now, when they're solving these, that's the doubling period. What they're looking for in this case is that p on the bottom here. Okay. What is the time it takes to get the double amount? So obviously this is not double, right? So the doubling period's got to be a little bit different. Everything's going to be here in hours. So let's just set up what we know. So we know that after a certain amount of time, this is how many cells we have. We started off with this amount, and we're doubling at a certain amount. Like I could solve for this and be a different number altogether by using 24 here, but we're looking for the period. Now this happened, I didn't write it in there, after 24 hours. 24 hours later, you see 24 hours later. So t is equal to 24 hours. So if I plug that into my equation, maybe I should write the equation out properly. I want to know what p-value I would have to put here. Make sure if I did the math on the right side, it equals 8,012. Okay, but I'm solving for something in the exponent. So remember, there's a couple of ways to do this. I don't have to rearrange it first. I can take the log of both sides and then use my log laws, but it's easier. It's not wrong to do it the other way, but it's just easier to move this over to the other side so I can have a nice clean exponent or exponential function. So I'm going to divide 8,012 by 3,000 or 387 here. Okay, so I'm going to get kind of an ugly number here. I'm just going to write that down over here. So 20.7 is equal to 2. I could probably write it down as a fraction, but I have the number in my calculator, so we're just going to use that. So it's to the nearest tenth of an hour. So when we solve for p, we'll figure that out. Okay. Now I want to solve for p, so I'm going to use my exponential function or exponential form here, change it to log form. So I got log base 2 20.7 there, and I drop the exponent down to be 24 over p on this side. I've got to solve for p, so I'm going to move the p up to the other side. I'll write out this step. And then divide over the log. Log base 2, 20.7. That's what p is equal to. So to the nearest tenth of an hour, so I'm going to go back to my calculator. I'm going to go 24 divided by log base 2. So I'm going to go math, log base 2. And I had the number there, so I'm just going to use my answer. So that's a second minus, pulls the previous answer up. You don't have to go, you can go up and select it as well. Hit enter. 5.4, well, nearest 10, so 5.5. 5.5, and this is in hours. So my period, doubling period is every 5.5 hours, I'm doubling. Okay. Just kind of the same kind of question here. It's just they're giving us the equation to start off with. It's telling us this is the half-life equation. H is the half-life of the materials. That could be like your P value. Everything's the same as some of the previous ones. And we're just asking for the length and time to the nearest day that will take 100 grams to decay to this amount. So we started off with 100 grams, milligrams technically. We wanted to know how long does it take to become 12.5 milligrams. All right, so we know the half-life of this is in days. So because this is in days, what we're going to solve for t is going to be the nearest day as well. Sometimes I try to mix it up and say, okay, half-life is in days, but how many weeks does it take, or how many years does it take to decay to something else? Yeah. Very similar to a question that we did before. You could just leave it in this form and take the log of both sides. Nothing wrong with that. Maybe I'll just do it that way this time, just to see what it looks like. I'm going to move this down and give myself a little bit more space. Okay. If I take the log of both sides, I'm going to go log 12.5. I'm going to just drop my units for now. Then I'm going to go log all of this, like that. Because I'm multiplying these two things together. I can't drop the exponent down yet because the 100 doesn't have the same exponent. But I can separate these two first. So this is the log of 100. And then plus, because I'm multiplying it, so I separate into two logs where I add them together. And then over here, we have log 12.5. Okay. Sneeze. Oh, I was going to sneeze. Okay. You realize that this is what's going to happen is that we are going to subtract over this log 100. Because I'm subtracting over the log 100, I would divide what's inside those two logs. It's like it's same as if I just start off by dividing by 100. It ended up being the same math that's over here. And then on this side, I would have this log all by itself, which means I can now drop this down into the front, and it becomes log 12.5 divided by 100. I guess I could have done the math there and said 0.125. And then I have t over 8 is equal to log a half. All right. So now what I can do is I can divide these two logs. I'm going to divide these two numbers first of all. Then divide this other log over. You get t over 8. And then we're going to times the 8 up to the other side. So 8 times a log of 0.25 divided by log a half is equal to t. Now this way, this is pretty much the only way you can do this question if you have one of the older style calculators that doesn't have a log-based change. You just take the log-based 10 of both sides and just go with it. Now if you can see down here, I'm dividing by log a half. So technically this could turn into 8 times log base a half, 1.125, using the change of base identity. So both those two sides of this equation are the exact same. I'm going to use the other side. I'm going to use this side over here. So I'm going to go 8 log 0.125, 8 times log. And and then I'm going to divide it by log of 0.5. So you get 24. So t is 24 days. It says do the nearest day, but it's exactly that many days. So I don't have to do any rounding or anything. Okay. Sometimes you get these compound questions. Remember we talked about these compound questions. Pretty much the only trick about these compound questions is how the interest changes. If it's like here, you can see it's compounded per year, per annum, but this is 5% per year, but it's compounded semi-annually, so that's twice a year. So my interest is not just 5%, it's 5% divided by 2, so it's 2.5%. My period is a half, because it's a half a year this will take place. If I'm assuming t is in years, like if I say t in years, then my period is half a year, right? That's my period. So I've set up my equation. So my principal amount, this is a P. My principal amount, there's a capital P, is how much you start off with. So $1,500. We are looking for how long it takes my number to double. So I want to know when this thing's equal to 3,000. So I set up my equation like this. This is going to be 1 plus my interest, remember correctly from before, t divided by p. You can put the interest number in there. Remember the interest you probably want to use in decimal form because I put 1 rather than 100%. Let's see what else we could do here. So we're going to divide over this number, get 2. This is 1.025. And t divided by a half. Okay. Yeah, I divided the 1,500 over first, but it's up to you when you decide to do that. I'm going to simplify my exponent. I'm dividing by a fraction, so you multiply by the reciprocal. You do a little flip, multiply, and now we're going to solve for t. This looks pretty easy. I've already divided over the 1,500 already. So I've gotten this, and it looks like a pretty nice exponential function. So I can change this into log form pretty nicely. So my log base, my base is not a nice number, but that's okay. 1.025 of 2 is equal to 2t. So remember when you do this, the exponent and these guys, they kind of switch their spots. This guy's inside the function. Now the 2 is inside the function, the t2 pops out. Then we're just going to divide by 2. I'll divide by 2. Okay, so let's go to our calculator, figure out what that is. So it's going to be a log base 1.025 2, and then we're going to divide by 2. So it takes 14 years. Let's put this over here. T is equal to 4. Is it exactly 14? Yeah, 14 years. Not quite exactly 14 years, but just slightly less than that. You may want to go 14.5 years because it's compounded semi-annually. 14 years is not quite enough. Maybe 14.5 years will guarantee that you have double the money, but you'll be pretty close. Because if I put that number back in here now, this is double check what 14 would actually do for us. Now, my equation right here, I want to see, do I actually double my money if I put a 14 in there? So 1.025 raised to the power of just 28. Not quite double our money. 1.99 times our money. Pretty close to being double. So let's just leave it as 14. If you want to be for sure to make sure you're doubled, you probably add an extra half a year on there to the next compound period. So 14.5. All right. So that finishes off decay growth questions, interest questions. There are a bunch of diploma style questions here. I want you to try these questions out. If you have any questions regarding these ones, give me a shout in my office hours. I'll post some answers for them at probably the same time this video is posted. All right. See you later. Bye.